Section 5.6 is the last section of Calculus 1. Woohoo! We made it. All right, substitution and area between curves. In the last section, we learned how to solve integration problems using the method of substitution, but those were indefinite integrals. Now we're going to see that when we have definite integrals, we don't have to go back to the x in the problem. We can keep the u, because usually it's a much more algebraically simple problem if the u is in the problem. And when we have bounds on our integrals, all we do is we take that lower bound in the original problem, plug it into what we let u be equal to, and that'll give us a new lower bound. Take your upper bound, plug it into what we let u be equal to, and that gives us our new upper bound, and we don't have to switch back to the x in the problem. Let's look at example 1 here. I think you're going to find that you like this much better. On this first problem, what will we let u be equal to? 1 minus r squared. What is du equal to? dr. But we don't have the negative 2r dr. What do we have? So this is going to be minus 1/2 du equals r dr. R dr. Okay. Sorry, way too much fun. So this then, according to Theorem 7, is going to give us the interval that goes from negative 1/2. What is, oh, by the way, this is going to be u to the 1/2. Our new lower bound I get by taking this 0 right here and plugging it in to the function that we let u be equal to. So that's 1 minus 0 is 1. 1 minus 0 is 1. Then to get our new upper bound, we plug the 1 in place of r in the function u, and we get 1 minus 1 is, okay, du. This says you take whatever u is equal to. We let it be a function of our variable of interest. Your lower bound then comes from plugging in that lower bound into the function. Our lower bound here was 0. We plugged the 0 in right here in place of r. 1 minus 0 is 1. Got it? That we changed our bound, so now we never have to look at the r ever again. So now we're going to integrate this. And by the way, how can I get rid of that negative there? Flip your bounds. Right? Because that's one of the rules that we memorized in 5.4. Okay. So this is going to be 1/2 times u to the, add 1, you get 3/2. Divide by 3/2, you get 2/3. And we're evaluating this from 0 to 1. So this becomes 1/3 times u to the 3/2 from 0 to 1, which is 1/3 times 1 raised to any power is 1, 0 raised to any power is 0. We end up with 1/3. Now, just to prove to you that this is a valid method, I am going to not change my bounds. After I integrate, I still end up right here at 1/3. But in place of the u, I'm going to plug in 1 minus r squared raised to the 3/2, and then go back to the original bounds of 0. Ooh, wait, we have a problem. I can't just do that because I flipped the bounds to get rid of the negative. I think we have to flip our bounds. Yeah, I got to put the negative here and then go from 0 to 1. Because I didn't flip, see right here I flipped the bounds. I got to undo that flipping because I'm keeping my original bounds. No flipping, keep the negative. You with me so far? All right, so this becomes, when I plug in my upper bound, this is negative 1/3 times, this is 1 minus 1 squared raised to the 3/2 minus 1 minus 0 squared raised to the 3/2. So far, so good? All right. 1 minus 1 is 0. 0 raised to any power is 0. 1 minus 0 is 1. 1 raised to any power is 1. And we end up with negative 1/3 times negative 1, which is 1/3. So whether or not we switch the bounds, if we change our bounds, we can stick with the u. If we don't change our bounds on the original problem, we have to go back to the original variable. To me, personally, I think it's easier to change the bounds. Arg. Example 2. All right. This is one we're going to have to do a u substitution on. Be careful. What do you think u should be equal to? Oh, no. No. Just cosine x, because what's the derivative of cosine? Negative sine. Du is equal to negative sine x dx. We don't have the negative, though, there, do we? So take out a negative du, and that's going to be sine x dx. Well, there's our sine x dx. So this is now going to be, when we rewrite this, negative 3 times the integral from, when you plug in a 0 right here, cosine of 0 is, and when you plug in a pi, cosine is negative 1. This is now u squared du, right?
Are you plugging in the original bound?
The original bounds in place of x in our function u. This right here was cosine of 0. This right here is cosine of pi. Now, I don't want that negative there, so I could rewrite this as 3 times the integral from negative 1 to 1 of u squared du. Right?
Where'd you plug in the pi at?
Into x. The 0 and the pi are the bounds that go with x. The negative 1 and the 1 are the bounds that go with u. Do you see why? Because if you don't see it, I need to explain it. This is the easiest part once you see it, but if you don't see it, you don't see it. This 1 came from looking at cosine of 0. That's where we got this new lower bound. And then we did cosine of pi, and that's where we got this upper bound. Clear? All right, I'm going to erase all that now because I don't want it on the notes, because I think it would be confusing if you're not watching it real time happen. All right, so we changed our bounds. Now, I want to point something else out. When we graph this function u squared, yeah, it is. And we look at the integral from negative 1 to 1. Oops. Let's do this. Negative 1 to 1. We're looking for the area of the shaded region, right? Isn't that going to be equivalent to 2 times the area from 0 to 1? Because we double the area, because this happens to be an even function. It cuts down on the arithmetic as well. Work smarter, not harder. It's easy to evaluate an integral with a 0 as a bound, right?
But how did you get this?
I know that y equals x squared. The graph of u squared is going to be a parabola. It's even. It's symmetric with respect. There's no horizontal shift here, so this is easy. If you remember algebra. Coming back to Hannes again. So this is 6 times 1/3 u cubed from 0 to 1, right? 6 times a third is 2 times u cubed from 0 to 1. Well, that's 2 times, plug in a 1 raised to any power is 1. Plug in a 0, this is just going to be 2.
Cool.
Looked complicated. All for a lousy 2. Not too bad. How convenient. Here's theorem 8. If your function is even from your integrand, then you can double the area from 0 to a, if it's even from negative a to a. If the function is odd from negative a to a, then the total area, because here we have positive areas, negative, negative, positive, they're going to zero out if the function's odd. So pay attention to even and odd functions. Your trig functions, cosine is even. Sine x is odd. Right?
Yeah.
Okay. Find the total area of the shaded region. Okay. I know it's going to sum to 0 if we look at the integral from negative 7 to 7, but I don't want to just look at the integral from negative 7 to 7. I have an area right here that is equal in value to an area right here. Right? It's just the opposite side. So what I'm going to do is I'm going to set up an integral that goes from 0 to 7, because that's this value right here, and I'm going to double it to get the total area of the shaded region. That's why when we were working that problem that we got the 0 correctly, I might add, by the way, after further discussion, I asked, were we asked to find the area under the curve, or were we asked to evaluate the integral? If you're asked to find the area, then you have to take the opposite of these negative numbers, because we actually want the area. Well, this area, because of symmetry, this area right here is the same as this area right here. It's just a different sign. Well, because I don't want to mess with the negatives if I don't have to, I'm going to double the area from 0 to 7. And my function here, we were told, is x square root of 49 minus x squared dx. This is how we set up the integral. Any questions about that? You're okay with that? All right. So we're going to do a u substitution here. What are we going to let u be equal to? Du then will be equal to minus 2x dx. So negative 1/2 du is equal to x dx. So a negative times a positive is going to give us a negative 1 u to the 1/2 du, because that negative 1/2 times 2 is negative 1. What is our lower bound going to be now? We plug in a 0 where? In place of the x squared. So 49 minus 0 squared is 49. Plug in the 7. 49 minus 7 squared is 0. How do I get that negative off of the integrand? So this is the integral from 0 to 49 of u to the 1/2 du. And when I integrate this, I'm going to add 1 to 1/2, we get 3/2. So that's 2/3 times u square root of u, because u to the 3/2 is u times the square root of u, from 0 to 49. Experience taught me to rewrite u to the 3/2 That's u to the first times u to the 1/2, isn't it?
Yes.
Well, there's u to the first times u to the 1/2.
Okay. Thank you for letting me know.
And I'll leave that one. Okay? So this ends up being 2/3 times, when we plug in our upper bound, we get 49 times the square root of 49 minus 0, because that's our lower bound. So this is going to be 49 is not divisible by 3, so this is going to be 98 thirds, oh crap, times 7. Square root of 49 is 7, so that, what's 14 times 49? 686 over 3. Is that right? Any questions?
Yeah, that's right.
And remember, you can always check 680 what? 6 over 3? You can always check your work by plugging in the integrals. All right, now, we've already discussed this, the area between two curves. What we do is the region between two curves, f of x and g of x, and the lines x equals a and x equals b can be represented or approximated using these rectangles perpendicular to the x-axis. Well, that leads us to the limit definition of the integral, and this is going to end up being the integral from a to b of f of x minus g of x dx, because the height of this rectangle is f of x minus g of x. The width is our delta x, it's our differentiable, and we're going from a to b because we're going to let each of these rectangles slide across this region from a to b. Well, that's a definition for the area of the region between two curves. So, in example 4, can we find the area of the region between the two curves here? And the answer is yes. Yes, we can. Are we going to integrate from negative pi over 3 to pi over 3? No, we're not. We're going to double the area from 0 to pi over 3 because we are going to work smarter, not harder. We can do that because of the symmetry here, right? Because if I were to fold this picture in half along this line right here, the left half here has the exact same area as the right half. So we'll just double our area of the right half because we like positive numbers better. What function is on top? 1/2 secant squared. So that's 1/2 secant squared t minus what function is on bottom? Minus 4 sine squared t dt.
Are you only subtracting it because it's negative? Why are you not adding them together?
When I subtract a negative, I'm going to add.
I understand.
It's upper function minus lower function. The lower function has a negative on it.
Gotcha. Cool. Thank you.
Let me do that. And then we rewrite this as 2 times the integral from 0 to pi over 3 of 1/2 secant squared t plus 4 sine squared t, but I need a power reducing formula because I don't know how to take care of that sine squared. Y'all okay with that? So this is going to be 1/2 times 1 minus cosine 2t dt. Correct? Now, just to make life good, I'm going to go ahead and break this into two separate integrals. So, multiply 2 times 1/2 and I get the integral from 0 to pi over 3 secant squared t dt plus 2 times 4 is 8 times that half is going to be 4 integral from 0 to pi over 3 1 minus cosine 2t dt. So far, so good? All right, when we integrate secant squared, what do we get? Tangent from 0 to pi over 3 plus 4 times, that's going to be t minus sine 2t times a half from 0 to pi over 3. So plugging in the upper bound, that gives us tangent of pi over 3 minus tangent of 0 plus 4 times, oops, wrong one, pi over 3 minus 1/2 sine of 2 times pi over 3, so that's going to be 2 pi over 3 minus 4 times 0 minus 1/2 sine of, can I just put 0? And that's all going to be 0 anyway, right? Tangent of pi over 3 is, you already said the square root of 3, right? Minus 0 plus, distributing the 4, that gives us 4 pi over 3 minus sine of 2 pi over 3. That's in quadrant 2, sine's positive. That's going to be 1/2, so that's 1/4, is that right? No, pi over 6 is 1/2. The square root of 3 over 2, so that's going to be the square root of 3 over 4 minus 0. Yeah. So this is going to be 4 square, oh, hang on. Let me drop this down. This is going to be getting it as one term, getting a common denominator. That's 4 square roots of 3 plus, 12 square roots of 3 plus 16 pi minus 3 square roots of 3 over 12. Well, 12 minus 3 is 9. So that's 9 square roots of 3 plus 16 pi all over 12. Not? That can't simplify. That's as simple as it can get. By the way, that's the exact value. And that's what I would want. Example 5. We have what, 10 minutes? We can do this. The instructions here are to find the area between the two curves. First of all, how many integrals will I have to set up? 2, because I have area 1 and area 2. Area 1 is going to be integrated from -2 to 0. Right? Because those are your bounds. We go from, strike that, -2 to 0. In this interval from -2 to 0, what function is on top? Because you take the larger value minus the smaller value. The function that's on top is 2x cubed minus x squared minus 5x minus the function that's on bottom, -x squared plus 3x. This is the function that's on top minus the function that's on bottom. That's how you get the height of this rectangle. Don't forget your dx. That's area 1. The function that's on top is this one right here, the pink one. It's pink minus purple in the first one. Plus, means I wrote too big, the integral from 0 to 2 of the opposite. This is going to be negative x squared plus 3x minus 2x cubed minus x squared minus 5x dx. Now, we can distribute negatives, collect like terms and all that good stuff to end up with the integral from negative 2 to 0 of 2x cubed. And then we have a minus x squared minus a negative x squared. That's going to be plus 2x squared. Minus 5x minus 3x is minus 8x dx. Plus the integral from 0 to 2 of, I believe we just end up switching the signs. This is going to be a negative 2x cubed. Yeah, negative 2x cubed, that's plus x squared. Nope, minus x squared. Those are going to cancel out. Oh, they canceled out over here too. Careful. That's a minus and a minus, that's a plus, that's a minus. These terms are gone. Screwed that up. So that's 2x cubed minus 8x dx plus the integral from 0 to 2 of, this is going to be minus 2x cubed plus 8x dx. So far so good? Now we actually integrate these a term at a time. So that means that we're going to add 1 to the exponent, making this 1/4, or I'm sorry, x to the 4th over 2 times the 4th, 2 minus 4x squared from negative 2 to 0 plus, add 1, so that's going to be negative x to the 4th over 2 plus 4x squared from 0 to 2. So now it's a matter of just plugging in the bounds, isn't it? When we plug in a 0, I'm going to do as much of the arithmetic as in my head as I can. I don't want to, I guess I should show every step. This is 0 to the 4th over 2 minus 4 times 0 squared. That's your upper bound. Minus the lower bound. So this is going to be 4 times, I'm sorry. It's going to be the lower bound of the 4th over 2 minus 4 times the lower bound squared. Lower bound here was negative 2. So far so good? That's this first one. I just need more space. Plus, on the second integral, we have upper bound, negative upper bound raised to the 4th over 2 plus 4 times the upper bound squared. The upper bound here was 2 minus the lower bound. So that's negative lower bound of the 4th over 2 plus 4 times the lower bound squared. And the lower bound here is 0. Now it's just a matter of cleaning up the arithmetic. This term right here is going to 0 minus, and then we have negative 2 to the 4th is 16 divided by 2 is 8. Negative 2 squared is 4. 4 times 4 is 16. Plus 2 to the 4th is 16 divided by 2 is 8. This is negative 8 plus 16 minus 0. All right, distributing the 8, this is going to end up being a positive 8. Yeah, 8 minus 16, and then you take the opposite. And this is 8 right here, so this ends up being 16. All right, examples 6 and 7 will have to wait until Thursday because they're completely different. So we're going to save this in parts, part 1 and part 2.